There's a 4 million solar mass shadow right next door. It's Sagittarius A star, the Milky Way's central black hole. The immediate takeaway is this: gravity there bends light into rings. Not metaphorically, literally, dust hides it from normal sight. Infrared and radio slip through, exposing the hidden engine. Tonight, we tour that engine calmly and piece by piece. Meet the stars that weigh it with clean orbital motions. Watch gas flicker while magnetic fields twist and channel heat. By the end, the center will feel close and real. Step outside on a clear night and face Sagittarius. The Milky Way bulge glows there, dense and gold. Behind that glow sits our galaxy's crowded inner neighborhood. Astronomers call it the Galactic Center, a turbulent hub. In plain words, it is the city center of stars. You should care because this district steers the whole disk. A central bar of stars channels gas inward along lanes. Gas follows oval paths, collides, and sheds orbital energy. Collisions thicken clouds and squeeze some into new clusters. Some gas keeps drifting inward toward the central black hole. Dust blocks visible light, dimming starlight by huge factors. Longer wavelengths slip through, revealing hidden structures and heat. Infrared shows stars through smoke with crisp motion. Radio unveils filaments and clouds shaped by magnetic fields. X-rays expose hot plasma near the edge of no return. Example: in real terms, the central molecular zone is vast. It spans about 500 light-years across the core. It carries tens of millions of solar masses of gas. The ring is lopsided, orbiting roughly 100 light-years. Inside that ring, densities fall while temperatures climb. Close in, only thin, hot plasma can happily survive. That plasma broadcasts mainly radio, which sails through dust. Common mistake is picturing emptiness. The center is messy. Another trap is imagining straight infall. Orbits mostly win. Net result: a bustling core hides behind curtains of dust. Now zoom in mentally to the radio source at dead center. Sagittarius, a star, anchors the core, quiet yet powerful. In plain words, it is a supermassive black hole. This matters because such mass sculpts orbits and tests gravity. Weighing it uses stellar speeds, tied to enclosed mass. Faster motion means stronger gravity and a heavier center. Independent methods converge near 4.1 million suns. That makes an event horizon about 12 million kilometers wide. Picture 8 Earth diameters swallowed inside dusty haze. From here, the shadow spans 52 microarcseconds. Imagine a donut on the moon, seen from your backyard. Despite the drama, our black hole barely eats today. The feeding rate is tiny, like nibbling a single grain. So the flow stays hot, puffy, and dimly radiant. Magnetic fields thread the plasma, steering streams and tapping rotation. Sometimes those fields snap and reconnect, dumping sudden heat. Hot spots brighten, orbit, and fade within tens of minutes. Rule of thumb: faster wiggles mean orbits closer to danger. Big flares can boost infrared by factors near 100. X-rays can surge similarly, then cool back toward baseline. Bottom line: massive, compact, and quietly restless describes this object. Shift your gaze to a tight knot of blue-white stars. These are the S stars, racing around the unseen anchor. They trace the gravitational well like precision test particles. You should care because those orbits weigh the center. We track positions and speeds, then fit clean ellipses. Relativity tweaks those paths, strongest near closest approach. The standout is S2, bright and well measured. Its period is roughly 16 years, looping the center. In 2018, S2 skimmed perilously close to the hole. The distance was about 17 light hours, remarkably near. That equals roughly 120 astronomical units. At periapsis, the star screamed at 7,600 kilometers. That speed is about 2.5% light. Its light stretched redward, showing gravitational redshift cleanly. The orbit also precessed, advancing slightly each cycle. Those details match Einstein's equations within measured uncertainties. Other S stars fill the map, each adding constraints. Together, they nail the mass and the central compactness. A dense star cluster would wobble and evaporate too quickly. Tiny test: could it be exotic boson matter instead? No, required densities exceed stability limits by absurd factors. Long monitoring reduces systematics, sharpening every parameter carefully. What to remember: real orbits point straight at Sagittarius A star. Now wander through a maze of glowing knots and dark lanes. This is the central molecular zone, warm and crowded. In plain words, it is the fuel reservoir for stars. You should care because reservoirs throttle engines over time. Gas streams inward along the galactic bar, then stalls. Stable orbits trap material, building a lopsided ring. Clouds slam together, heating and losing angular momentum. Some collapse into clusters, igniting bursts of star formation. Shock fronts carve bright edges, marking energy lost in crashes. Magnetic fields lace the region, drawing ruler-straight filaments. Those threads stretch dozens of light years, astonishingly aligned. Electrons spiral along them, emitting radio as they turn. Some filaments gather like harps, hinting at past outbursts. Example in real terms, the zone spans 500 light-years. It holds several tens of millions of solar masses. Typical temperatures range from tens to hundreds of Kelvin. Starbirth there is bursty, not steady, across million-year cycles. Occasionally, a cloud decays inward, leaking material deeper. Density drops inward, while temperatures and ionization rise. That inner plasma glows mainly at radio wavelengths. Bottom line, the ring stores fuel and schedules feasts. Every so often, the quiet center twitches and brightens. A flare is a brief spike in infrared and X-rays. It matters because flares expose physics near the horizon. Magnetic fields can reconnect, dumping heat into orbiting clumps. Hot spots brighten, orbit, and fade in tight loops. Close orbits complete in tens of minutes, matching wiggles. During big events, infrared can jump by 100. X-rays can echo that surge, then fade smoothly. Most days, the hole only sips, flickering faintly in radio. Rarely, a whole star strays too close and shreds. Tidal forces stretch it, launching streams of colliding debris. The wreck heats violently, glowing for months or longer. We have not seen such a feast in modern times, but the galaxy bears scars from past overeating episodes. Two giant gamma-ray lobes rise above and below. These Fermi bubbles tower 25,000 light-years. Winds or jets likely inflated them a few million years ago. They cooled into hazy domes, still hanging above us. So the center cycles between nibbling and belching over eons. Capturing the shadow itself required a trick as big as Earth. Radio dishes worldwide linked together, acting like one telescope. That technique is very long baseline interferometry, or VLBI. You should care because only that resolution separates the ring. At millimeter wavelengths, the target spans 52 microarcseconds. Think donut width, perched on the moon's dusty plains. Signals arrive faint, weathered, and scrambled by drifting electrons. Interstellar plasma blurs the view like frosted glass. Teams correct that blur statistically, anchored by other probes. Time adds another hurdle, the ring flickers within minutes. Standard imaging assumes stability, which this target defies. So researchers reconstructed movies, constrained by physics and closure phases. In 2022, the reconstructed ring size matched gravity's prediction. Its diameter fixed the mass, agreeing with stellar orbits. Brightness around the ring looked uneven, hinting at rotation. Polarization maps traced strong fields threading the plasma. Those fields align with frameworks that can launch jets. Example in real terms, orbit times near 30 minutes fit. That timing matches hot spots skating near the stable orbit. Common mistake is expecting a crisp photo, not statistics. The image is a constrained solution, checked against physics. Net result, we glimpsed the silhouette and its organized flow. Step back and ask what this black hole means here. It dominates only a small sphere, just a few light years. Outside that bubble, the nuclear star cluster sets gravity. The wider galaxy barely notices, except through slow feedback. You should care because feedback sculpts starbirth over ages. Outflows and past bursts heat the halo and stir gas. Depending on timing and geometry, bursts quench or trigger. For Earth, its pull is no threat at all. We sit about 26,700 light-years. At that range, its tidal force on you is negligible. Even dramatic flares bathe only the central few parsecs. Day to day, the sun affects you far more. In the far future, galaxies will still dance and merge. Andromeda and the Milky Way will tangle in 5 billion years. Their central black holes will spiral together, radiating gravitational waves. The energy rivals many supernovae, integrated over long time. The merger remnant will host a heavier, settled hole. Meanwhile, clusters can sink inward, lighting new starbursts downtown. Occasional supernovae will enrich gas, seeding heavier elements. Bottom line, the heart beats slow, yet sets our rhythm. We started with a hidden shadow at our galaxy's heart. Now you know its mass, ring, and restless habits. You have seen stars weigh it and gas feed it. The core is no void, it is a living laboratory. It turns gravity into heat and sky scars into clues. One sentence recap: a small engine shapes a giant system. If that picture sparked wonder, journey with me again. I share calm, deep space stories every single week. Tap subscribe if you want the next launch here. Until then, look up and feel that distant hum.